Our next speaker is our co-chair, Hari Mukundarajan from Stanford, and the title of his presentation is Sesame for Mosquitoes, Crowdsourcing Vector Surveillance Using Mobile Phone as Mosquitoes Sensors.
Thank you. So I know the priority in this session is really how to get rid of mosquitoes. But they can be pretty cool in a couple of ways. For instance, they're the absolute champion in the insect kingdom when it comes to their sense of hearing, which operates through their antennae. And this is important because hearing is the fundamental underpinning of their mating choices. Mosquito sound is sexually selected in the sense that the male mosquito has to listen carefully to the wing beat frequency of the female mosquito and reproduce it. Not exactly, but in a 3-to-2 ratio for the female to even consider mating with that male. So the guys really have to listen to the girls in this case. It thus functions as an attractor for males and also as a pre-mating isolator for species, making it unique to every individual species. The attractive properties have already been exploited in a number of traps, where traps baited with female mosquito recordings attract a lot more male mosquitoes than traps that are not baited with sound. But what about using sound for surveillance? It's species-specific, it's non-invasive, and it has the potential to be extremely high throughput. You do not need to PCR a huge bucket of mosquitoes to identify all of them. So why isn't this a thing yet? And the answer really lies in the sensors that you need. Acquiring the soft hum of a tiny insect against background noise really requires extremely sensitive microphones. Like this one, for instance. This is a studio microphone. But this thing is fragile, sensitive to the elements, and I can tell you it's pretty expensive. This is not something I want to put in my backyard to listen to mosquitoes. There's been a clever couple of workarounds where people have used optical wing beat detection as proxies for sound and integrated these into traps for automated mosquito detection. But the challenge still remains that you have to build these units and you have to build them into traps and distribute these traps, and traps can still be a little expensive. So can we bring down these costs to such an extent that surveillance of this sort can become ubiquitous and you can actually generate huge amounts of data for data mining or predictive machine learning or any other big data analysis? Like, for instance, can this map a hypothetical illustration of spatiotemporal activity of different species in real time? Can we make this reality? And the solution that we propose lives in the pockets of each and every one of you sitting here today. It's the mobile phone, an exquisite acoustic sensor built to very high specifications with a robust network spanning 5 billion users and rapidly growing infrastructure, presenting almost a zero-cost solution for data acquisition and transmission. So all a person has to do really is to record mosquito sound and transmit it, and maybe we can have that map. But in a lot of the areas where surveillance is really relevant, people don't really have these nice Sony Xperia phones or other smartphones that I've just shown you here. What they have instead is this little brick that was fashionable when I was an elementary school student. So is this good enough to record mosquito sound sensitively enough? If you're feeling a little skeptical at this point, I'm going to convince you by playing a recording of Aedes aegypti mosquitoes infected with Dirofilaria immitis taken 2 days ago with this phone. That's not a pleasant enough sound to go on, but I just want to let you know that every single piece of data I'm going to show in this talk has been acquired with this phone. So what next? All you have to do first to acquire this sound on your phones is to identify the primary microphone orient it towards a mosquito, and then just bring it close to the insect, and voila, it acquires sound. It really is as easy as that. And the mosquitoes can be either free-flying, or they can be trapped in something like a plastic bag, or they could even be in cages. And once we acquire sound, we analyze this by acquiring the frequencies, parsing out the frequencies at every instant of time to create a spectrogram from which we then parse out the distribution of the fundamental frequency or the wing beat frequency of the mosquito in each trace. Now, how do we know that this sound is actually good enough for the analysis that I just proposed? So there are two main qualities to every sound wave. That's the frequency and the amplitude. And we evaluate both of these by looking at the fidelity of the spectrum and also the signal-to-noise ratio of whatever is acquired by the phone. For spectral fidelity, we calibrate this by setting up a phone against a non-acoustic measure of the mosquito's wing beat frequency. In this case, a camera recording flight at 10,000 frames per second. We then get the wing beat frequency at every instant of time by counting the number of video frames it takes per wing beat and align this with the sound with an accuracy of 100th of a second. And here, the green trace shows the video, the red trace shows the audio, but what you see is yellow, showing a perfect alignment in the frequency domain of less than 5 Hz, or less than 2% of base frequency that we measure. So yes, the frequency is pretty accurate, but how close do you really have to get to acquire these faint sounds? And we calibrate that with these fancy studio microphones, which are a gold standard in recording insect sound in laboratories. So from this curve, which is, we showed 3 graphs, the first one for this brick, the second one for a mildly obsolete iPhone model, and the third one for this nice Android smartphone. And you can see that mobile phones actually are not bad at all in comparison with fancy studio microphones. They're optimized, of course, to be held close to the source of sound when you speak into them. So at 10 millimeters from a mosquito, they're fantastic. As you get farther away, it really depends upon the model and its frequency response characteristics. But in general, most phones do pretty well a distance of about 50 millimeters or 2 inches away from a mosquito in typical ambient noise environments. So given that they have a little bit of difference in their frequency response, it's really important to know that the frequency they capture is actually equivalent for different mobile phone models. Otherwise, you do not have the basis for something that can be truly global and that anybody could use to produce comparable data. So we show using 8 different models, including 4 smartphones and 4 feature phones, that all phones really produce a very tight and similar distribution. And you can see the statistics here that these are all mostly identical in the kind of frequencies they measure in a population of caged Anopheles stephensii mosquitoes. Similar is a qualitative term, and we go ahead and quantify this through statistical metrics. We show the overlap distance between the distributions to be very close to 100%, and at the same time, the information divergence between these distributions is less than 20%. So less than 20% does this set a lower limit for how different species should be in their frequency distributions for detection? And is this really the case? That's the next question we investigated, and it turns out that conveniently for us, species do have very distinct frequencies. The statistics for frequency here for more than 50 mosquitoes in cages on the same axis as the previous graph show considerable divergence with respect to what you get from a single phone for a single species. And when you quantify this using exactly the same metrics, you see that divergence between distributions is extremely high, exceeding 80% in most cases, except with some exceptions. I'll first look at the divergent case. The bottom 2 bars, the pink and the purple, they indicate Aedes aegypti and albopictus females respectively, and the thick rectangle shows where the majority of the distribution, between 10 to 90%, is concentrated. And you can see that in the field, with just your mobile phone, you can easily tell instantaneously whether a mosquito is an Aedes aegypti or albopictus female. But on the other hand, in cases where you cannot distinguish species, what a mobile phone gives you for free, along with sound, is metadata, a timestamp, a location stamp, sometimes even images. And in this case, where you have Aegypti and Anopheles albimanus, which are both co-occurring vectors, all you have to do to separate them, even though they have similar frequencies, is to look at the timestamp on the recording and parse out day-biting Aedes aegypti from the night-biting Anopheles albimanus. So we went ahead after the lab tests and did a bunch of field tests as well, and this video shows us recording mosquitoes in the field. The good thing about them is that we don't have to find mosquitoes. They find us. And a lot of these recordings take place under a variety of background noise conditions, from fire trucks to bird song to human speech. And we can actually parse out the mosquito sound in most of these, despite these background conditions. One important question to consider: we did a lot of lab tests, which I showed you with tight distributions, with mosquitoes that have been bred in laboratories for generations. How good is that when compared to field mosquitoes, which are so divergent in their larval habitats and size and age and blood feeding status? And the answer to this, happily for us, is not at all. These Aedes syrensis mosquitoes caught in the wild vary over twofold in terms of their body size, but the morphology seems to have absolutely no effect on the wing beat frequency, making this a fairly universal measure for detecting a certain species. And we see the same thing in 50 specimens of wild-caught culex, where the variation within a flight trace due to flight maneuvers is actually much wider than the variation between individuals. So having done tests in both the lab and field, we now tested its capacity for ecological mapping by getting 13 volunteers, asking them to take a hike in a park and record mosquitoes around them. And this is Big Basin State Park, an area of 3 kilometers by 4 kilometers, mapped using mobile phones. And you can actually see spatial variations in mosquito population density, even just half a kilometer apart on the same hiking trail. You can also fine-grain this data in time. At 6 p.m., there were not many mosquitoes, and at 7, there were so many we were bitten to bits, and at 8, they thankfully started going away. We repeated this exercise at a field site in Madagascar, where there are two main genera, Culex mosquitoes and Anopheles, which happily for us have a significant difference in their frequencies that allow us to map out within that village field site the gradient for different species of mosquitoes in a multi-species ecological mapping. Here you can see that towards the west, the yellow squares show Anopheles, which doesn't exist in the east of the village, but in the east, you get sporadic collections of Mansonia, which we do not see in the west. You can also see spots where in one house there are plenty of mosquitoes, and just a couple of houses away, you just get no mosquitoes at all. So this is fine graining on a scale of a few tens of meters. And of course, with a mobile phone, the time resolution is on the order of minutes or seconds. So where do we go next with this? We plan to start an initiative that we call a buzz, where we're currently building the infrastructure to collect data from beta testers at different sites in the world and automate the processing of this data to identify species, build up a database of species in different areas, and start integrating this into vector maps. Eventually, we hope to scale this up into a citizen science initiative where anybody, any of the 5 billion users on the planet, could just whip out their mobile phones, record the mosquitoes around them, and contribute to surveillance and the war against insect-borne infectious disease. So in a nutshell, I hope I've convinced you today that you can be mosquito hunters too. Mobile phone microphones are sensitive enough to pick up mosquito sound, which are species-specific enough to help in identification, and hopefully, by aggregating data from a large number of users at zero additional cost, we could hope to build large-scale ecological maps with extremely fine spatiotemporal resolution someday. I'd like to acknowledge all the people who've supported our work and all the wonderful people who've helped us along the way as well. And with that, I'd be happy to take any questions. So I'm not sure we really have any time for questions specific to this talk. However, yeah.
I was just wondering, so when people using that, how long do they need to switch their telephone on? And another question is, do you have any, have you actually tried to test out the app and people are responding to that?
Those are great questions. One is how long we need to keep the sound recording on, and the second, have we already tried to do this with others? So question one, the amount of sound duration that we actually need to identify the species is about 1/20th of a second. So 50 microseconds is all we really require from the processing side. However, the longer the sound trace, the better it is for us to make the ID because it's much more robust. And it's not really about keeping the app on all the time. It's more like you find a mosquito, you just use your recorder, and then you go after it. So typical traces we get from the field are about anywhere between half a second to about 5 seconds. And that makes for a great data trace for us. As far as your second question is concerned, it's not really an app yet. We're still working on building on it. All the data we've collected so far is on pre-existing voicemail and voice memo apps that already live in mobile phones. We have tried gathering volunteers, however, especially in Madagascar. We worked with staff from an NGO. I think it's a little difficult at first because people don't really believe they can do it. But we found that when we work together with them and do a team coaching session, then it's quite easy to get people to pick this up within 5 or 10 minutes, and they're just producing their own data. And then, there's like a multiplier effect where users train new users who train more users, and so on and so forth.
I have my experience with using a GPS tracking app that I developed, and I'm happy to share my experience with you.
That would be wonderful. I hope we can talk. Thanks. So the speaker for the next session will not be here since the abstract is withdrawn. So I hope we can throw the floor open for a general discussion for questions for all the speakers. I'd like to invite all the speakers to come up so that we can just take questions from the audience.